Okay, so here's the cyclic quadrilateral quadria theorem that we've introduced as a replacement for the Brahmagupta and Robbins formulas, expressing the quadria of a cyclic quadrilateral in terms of a quadratic equation involving two quantities which are obtained from the four quadrances of that cyclic quadrilateral, and these things intimately connected with the quadruple quad formula. So a natural question might be, why is this a quadratic equation? If we're given four quadratas, surely there's more than just two possible cyclic quadrilaterals that we can cook up by rearranging these line segments in different ways, some convex and some non-convex. So let's have a little look at that. It's an interesting aspect of this story. So let's switch to A, B, C, D in terms of side lengths and go back to Brahmagupta's formulation of things. So here is a cyclic quadrilateral with sides A, B, C, and D. And here is another one with the same side lengths. And what we've done is we've sort of reshuffled the order of these line segments around in the same circle. Why is it that the areas of these two things are going to be the same? So here's a relatively easy argument. So the area of this quadrilateral is the union of these four areas. Here's the center of the circle. Each of these are isosceles triangles because one of the sides is a radius of the circle. Okay? So this quadrant and this quadrant are equal. All these four quadrants are equal. And that means that this triangle here, which we've denoted A, and this triangle over here, denoted A, are actually the same triangles. They're congruent triangles because these two sides are both the quadrants of the circle, and here this length and this length are the same. So these areas match up, and these two areas match up, and these two areas match up, and these two areas match up, and that allows us to see that even if we reshuffle the orders of these four line segments along this circle, that the actual area or quadria of the cyclic quadrilateral doesn't change. So as an exercise, you can convince yourself that this is also true in the non-convex case. It's a little bit more subtle there. So here is a non-convex quadrilateral with sides lengths A, B, C, and D. Okay, and I've drawn the same kinds of triangles emanating from the center. Just join the various four vertices with the center. So I have these four isosceles triangles. So that would be one, and this very narrow one here would be another, and then this one here would be another, and then this one here would be another. And over here I've used the same size circle and rearranged these line segments. So there's A there, and this D I've moved over here like this. This B here I rearranged to go up here, and C is arranged to go here. You might say, how does one know that we can actually do this? Well, you can deduce this from the positions of these triangles. So you have to think about this triangle A and this triangle D. So that angle and that angle, the classical sense, and that angle they are going to be the same. And they're going to be the same as this angle here, the B triangle, together with this angle here in the C triangle. Over here, there's the B one, and there's the C one. All right, so I give some thought to this situation. So this is illustrating the idea that even though we can, in fact, use the same circle and create different looking quadrilaterals with those same four side lengths, be it convex or non-convex, the areas are not going to change. Okay, the areas are not going to change. And that's why there's really a quadratic equation in this cyclic quadrilateral quadria theorem and not some higher degree equation, because there's really only two possibilities for the quadria of the quadrilateral given the quadrances of the four sides. So I want to show you how this new theorem incorporates the Brahmagupta and Robbins formulas. It's kind of a restatement or way of putting them together. And it really relies only on the arguments that we've had in the last video. But this is really only a temporary proof, because ultimately we want to establish this result independently of any prior theory of real numbers, any notions of square roots and distances and lengths. So we are going to have to come up with a completely independent proof of this. But in the meantime, this is a way of connecting it with the formulas of Brahmagupta and Robbins. So here's our quadrilateral, A1, A2, A3, A4. I've drawn it as a convex one, but it's not necessary that it's convex. Here are the side lengths A, B, C, D, and we'll use that notation as well as the quadrants formulas, so that the quadrants Q1, 2 is just A squared, Q2, 3 is B squared, Q3, 4 is C squared, and Q1, 4 is D squared. Okay, so Brahmagupta's identity, which was what we got when we looked at the quadruple quad formula applied to these four quadrances as squares of distances. Now we saw that that factored into a product of 8 factors. And the first 4 we can group together as A1, and the second 4 we can group together as A2. And let me call this P for a later reference. Okay, and here's the kind of formula that we obtained for A1 and A2. So A1 was, remember, part of the difference of squares, and it was some formula like this. Actually, we were using a asymmetrical form instead of this one, so I'll replace that now with a symmetrical form. So there was some quantity involving the A's, B's, C's, and D's all squared, so I'm replacing them with just these quadrances, and then plus 8A, B, C, D. Perhaps you can remember that. That was essentially the Brahmagupta's formula for the quadria, of a convex cyclic quadrilateral. And then the second factor, product of the next 4 terms, had a similar kind of expression, but with a minus sign, minus 8A, B, C, D. And that was essentially the quadria of a non-convex quadrilateral, and that was basically Robbins' formula. So I'm rewriting things from our last video. Okay, now what we can do with these two things is, first of all, we know that their product is, well, we're calling it P, which is this quantity right here. What we can also observe now that if we take the sum of these, the sum, then these two terms here will cancel, and we'll just get this term here times 2. Okay, so what is M? Well, M is just this quantity right here. Okay, so we get that A1 and A2 are two quantities whose sum we know, which is 2M, and whose product we know is P. Well, that means that A1 and A2 in fact satisfy a quadratic equation of the form A squared minus 2MA plus P equals 0. Because I reminded you that if you have a quadratic equation of the form, say x minus r times x minus s, okay, then the last term will be the product of r times s, and what's inside here will be negative the sum of the two zeros, r and s. So this quadratic equation, which is really the cyclic quadrilateral quadria theorem, it's a way of putting together the Brahmagupta and the Robbins formulas to eliminate any dependence on A, B, C, D. So now these quantities M and P only depend on the Q's and not on the A, B, C's, and D's. Okay, because the sum of these two things was 2M, so this is just M, and the P was just this quadruple quad function applied to these 4 quadrances. So it's now a purely rational reformulation of both the Brahmagupta and the Robbins formulas sort of at the same time. And circumventing now any need for a discussion about convex or non-convex, both cases are covered by this one. So now let's do the same thing that we did for the Brahmagupta and Robbins formulas. Illustrate the theorem by looking carefully at a concrete example where we can see everything laid out. So we are adopting a rational point of view. We're going to not use any floating point arithmetic. We want full integer arithmetic at all times. Here's our unit circle, which is what we're going to use, and we have to have 4 points on it. And I'm going to choose 4 rational points on the circle, which are roughly in the same kinds of positions as the real number example ones that I did before. Okay, roughly, but not exactly. So A1 will be the 0.10. A2 will be up here. It'll be the 0.3/5, 4/5. We recognize this is a point that's exactly on the unit circle because 3 squared plus 4 squared equals 5 squared. That's our favorite Pythagorean triple. This point A3, we're going to choose it to be minus 12 over 13, 5 over 13. We recognize another Pythagorean triple, 5, 12, and 13. And over here, A4, we're going to choose 15 over 17 and minus 8 over 17. There's another Pythagorean triple, 8, 15, and 17 there. Now, we know how to rationally parameterize the circle. Right? Let me remind you that if you take any rational number t, then you can cook up a corresponding point on the circle by choosing 1 minus t squared over 1 plus t squared to be the x-coordinate, and 2 times t over 1 plus t squared to be the y-coordinate. So I don't have to choose simple ones like this. I have a whole wide variety of points that I could choose pretty well anywhere I want to be points on this unit circle with rational coefficients. Okay, what's the next ingredient? Well, here's our quadrilateral. And we want now to calculate the quadrances. Note that I'm denoting the quadrances here with a little rectangle along the sides, alerting us to the fact that we're working with quadrances and not distances. So Q12, how do we calculate that? Well, we just take the difference between the x-coordinates and square it, the difference in the y-coordinates and square it. So that'll be 2/5 all squared and 4/5 all squared. That'll be 2 squared is 4, 4 squared is 16. You add them together, you get 20. So 20 over 25, which is 4/5. And similarly, you can work out that the quadrants between these two will be 162 over 65. The quadrants between these two will be 882 over 221. And the quadrants between A4 and A1 is 4 over 17. Okay, so we got those 4 quadrances. Now we need these two quantities, P and M. P was the quadruple quad function applied to these 4 quadrances. Okay, so that was that biggest formula that we've seen that comes from the geometry of the line. It's the relationship between the quadrances of the 4 points on a line. Okay, we know what that is. We can calculate that. I get my computer to do it, and I get that number there. It's a biggish fraction, but that's what we expect when we're doing this kind of rational number arithmetic. And the quantity m, well, that was this expression here that we saw in the last few slides. And that turns out to be this quantity right here. So m and p are going to be the ingredients to create this quadratic formula for the quadria of this quadrilateral. 16 times the area squared. So let's see what that looks like now. Alright, so the quadratic equation that we get looks like this. A squared minus 2ma plus p, and that's going to be equal to 0. It's a quadratic equation. So we naturally ask, does it factor? Well, it turns out it does factor. Okay, so it's a pleasant fact that if we get rid of this denominator out front here, then the 2 linear factors are these ones. And then we get 2 solutions. One of them is, let's see, 1,065,024 over 48,841, which is approximately 21.8094. And then the other one is minus 21,312 over 244,205. These are the 2 solutions to this quadratic equation that the cyclic quadrilateral quadria theorem gives us. So what's the significance? Well, this is the actual number that we want. This is 16 times the square of the area of this quadrilateral. And I remind you, this is not too far from the real number example that we got when we looked at some real points close to being on the unit circle, which formed a quadrilateral roughly in a similar kind of position. I think that was around 19. What's the meaning of this? There's a negative sign here. We're getting the other possible quadria to be negative. This is supposed to be 16 times the area squared. How can that possibly be? The algebra is telling us that these four quadrances form a convex quadrilateral, namely the one we had there. But if we try to form a non-convex cyclic quadrilateral using those same length segments or same quadrants segments, we are not going to be able to do it. That's why we're getting a negative number here. It's the algebra telling us that the other case, which is the non-convex one of Robin, in this case doesn't exist because of the particular relationships between the four quadrances that we've chosen. So there's something else that we should do here. We should look at the analog of the Robbins formula. So looking at a non-convex cyclic quadrilateral, and we can try this one, A1, A2, A4, A3, and you might like to work this out as an exercise before I'm about to show it to you. Okay, so if you like this kind of algebra, you have a computer there, you're happy to make some algebraic calculations, see if you can work this out and see if we're going to get the same answers. And let's just remind ourselves that we still do need a correct proof of this cyclic quadrilateral quadria theorem. Okay? That's still something that we owe you to see. So we are going to come back and do that in some later video. So now let's have a look at this non-convex situation and see that the Robbins formula is actually also incorporated here into this, this kind of formulation. All right, so let's have a look at this non-convex situation that I asked you to do in the previous exercise. So here we have A1, A2, A4, A3, same points as we had before. So that's the point 1, 0, that's 3/5, 4/5, that's minus 12 thirteenths, 5 thirteenths, and this one 15 17ths and minus 8 17ths. So now the four quadrances are these ones here, and here they are right here. And the quantity P, which is the quadruple quad formula, acting on these four, gives us this number. The quantity M, which is their sum squared minus twice the sum of their squares, turns out to be this one. And here is the actual statement of the theorem that the quadria of this cyclic quadrilateral satisfies this quadratic equation with this is the M and this is the P. Let's have a look what happens there. Okay, so this is what ends up happening. Here is the quadratic equation given by our theorem. There's the M value, there's the P value, and after common denominator is peeled off, then it factors as a product of linear factors very pleasantly, and the two solutions are then this number, which is approximately 1.78, and this number, which is approximately 74.7. And in this case, the answer that we want is this one here, which is not too far from the example that we showed you in the real case with similar position points. This one here is exactly the same as the quadria of this cyclic quadrilateral. So it turns out to be exactly the same. The formula for the quadria is 16 times, and then there was that quantity involving x1, y2 minus x2, y1, where you take the four coordinates and substitute it into that sort of alternating expression and square it. All right, so you do that, you get exactly this number here, so we can verify the theorem exactly in this example. You can see many advantages in working in this rational, concrete, logical way. It's definitely a big step up from the ambiguity and the imprecision of working in real number arithmetic. Here's a bit of a fun challenge for you. Can you find a convex cyclic quadrilateral with the same quadrances, which has this quadria? Okay. The other solution in this case does have some physical significance because we can in fact find, at least approximately, find a cyclic quadrilateral, perhaps with a different size circle. In fact, almost certainly with a different size circle because its quadria is much bigger. Okay, that has the same quadrances, but it's a cyclic one. Okay, so a bit of a challenge to find that and to make sure that you get exactly the same thing with exactly the same quadrances. Okay, so that's been very exciting. We've established a new way of thinking about a very classical result. We've reconfigured things so that the ambiguity or the dichotomy between the Brahmagupta and the Robbins formulas are now sort of incorporated into the single quadratic equation. So the algebra is somehow taking care of these geometrically perhaps different situations at the same time. So it turns out that this way of thinking, this kind of formula, has in fact in the last few decades been found very useful, not just in planar geometry, but also in planar geometry, but also in three-dimensional geometry. Okay? So next time I want to, just sort of in the spirit of investigating these kinds of ideas, I want to talk a little bit more about some additional lovely formulas of Robbins, having to do with the area of cyclic pentagon and hexagon. And I also want to talk about some remarkable work that's involved with polyhedra, something called the bellows conjecture, and a very lovely theorem of Sabatov. So that'll be quite interesting stuff, some of it not very old at all, in fact. And you can see that the same spirit of working rationally is in fact naturally adopted by many modern practitioners in this branch of geometry. So what we're doing here would not be considered particularly novel at all by certain modern geometers. Right? So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.